right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are doing great. Um, let's actually jump into it. Uh, okay, so where have we been? Let us remind ourselves, me included. This week has been crazy, and I think I kind of ran myself to the ground a bit, kind of keeping up with everything. So I got some sleep last night, probably not as much as I needed, but now it's like, what happened last week? It's like, I'm like, totally, what did I say to these people? What did I do? Did I do anything? Did I say anything? Like, I don't know. Like even last class, like you may have noticed that the video I posted in your playlist was actually a playlist for another class, the class I had after you guys, because somehow I managed to even record things incorrectly. Like I accidentally recorded to my computer and it recorded the gallery view somehow, and like I can't post this, so I just kind of hope no one would notice. Post the video for the other class and the notes for the other class. Like they probably won't know. Yeah, but these are, I think these are your notes. Maybe not. Yeah. Okay. But let's get into it. So, and this is also the nice thing, you know, life lesson about being prepared. So it's like I already prepared the examples I wanted to talk about a long time ago. Of course, I don't remember what I prepared, but it's nicer to have something to go off of, so I can know what Jhevon was thinking last week. Oh yeah, that's what I wanted to talk about. But let's do it. Actually, a very interesting topic, and maybe I'll talk about it in 5.3, just about how interesting it should be. But we started chapter 5. We started talking about linear inequalities, which are kind of like equalities, but only on the boundary. These guys take things a little bit further. They have a range of possible answers as opposed to like a few. So we looked at a linear inequality. These were just guys that have one of these forms. The solution to those inequalities are all coordinates, x and y, that would make them true. So if I plug in x and y into any one of these guys, and I would get a statement, something is greater than something, or something is less than something. And if that statement is true, then that xy coordinate is in the solution set of the inequality, right? So that's how the solution, but we are more interested in being able to graph the solution. And so that's why I taught you guys. So just as a reminder of that, what you first do is you graph the line that they represent. If it's a strict inequality, you graph it by a broken line. If it's a less than or equal to or greater than or equal to, then you graph a solid line. For the most part, in our applications, it's going to be solid lines. Then what you're going to do is you're going to determine the region of space that solves that inequality. It turns out that the line is just going to split space into two parts, and you're just going to figure out, well, which part gives me the answer. And you can do this in a couple ways. You can just test a random point, pick a random coordinate in one of the parts, plug it into the inequality that you have. If it's a true statement, it means that that coordinate that you picked is in the solution set. So every coordinate in that region is in the solution set. You shade that whole region. If that coordinate that you picked plugged into the inequality does not make sense, it says something like 5 is bigger than 11 or something like that, then you're like, oh, that's not where the solution set is. I need to pick the opposite side. So that's one way. Another way is to rewrite it in a certain form where you actually isolate the x or the y, or sometimes it's actually given to you in one of these forms, and so you can just immediately apply this. But without calculations, if it's written in this form, you can know if given a line, should I shade to the well, I don't know if my video is mirrored, but this is my right. Should I shade to the right or the left, right? And you can know that by the inequality sign that results when you isolate the x or the y. So there's also that option. So we did that, and we tested a bunch of things, and we figured out how to graph the solution for a single linear inequality. So now what we're going to do in the next section is put this on steroids. We're going to actually do this for several inequalities at the same time, and this is called a system of linear inequalities. So let's actually see what that's about. And someone's trying to get in here. Let me let. Okay, so in the last episode, these were the guys we were faced with. These were the guys I wanted you to try. So it's just me recopying the examples. But first, apparently, Jhevon last week had the foresight of saying, you know what, I probably should tell them some definitions at this point. So I am going to believe that I wrote some things down that I'm like, oh, they should probably know this. I did. Yeah. Yay, Pastor Jhevon. He doesn't always do great things, but sometimes he does. Sometimes he does good. Sometimes like, oh, Jhevon. You know, sometimes Jhevon is like, this is a problem for future Jhevon. And then I go like, why didn't I do that? Sometimes though, I'm like, yeah, it's good that I did this. Go past Jhevon. All right. Let's talk about some definitions. We are talking about systems of linear inequalities, so let's talk about that. Definition. A system of linear inequalities. Why does that seem so thick? I don't know. Maybe did I change the pencil settings? Okay. I don't know what Pastor Jhevon did, but messed up. You can't trust that guy. Okay. Let's leave it. Definition. A system of linear inequalities is a set. We're actually going to talk about sets in detail at some point, in some detail, of linear inequalities considered together. The solution is the set of all points xy that make all the inequalities true simultaneously. By the way, this solution may not exist. It's possible. Of course, in this class, often it's going to be something that exists that I want you to find. The solution may not exist. Silly example, like if I have the system, x is strictly bigger than 1 and x is strictly less than 1. Yeah, no answer, dude. Like you're requiring something that's impossible, right? So if that's a system, it has no solution, right? I can't find something that's both strictly bigger than 1 and strictly less than 1 at the same time, right? I can find something that's less than or equal to 1 and at the same time greater than or equal to 1. Yeah, 1 itself, but I can't actually satisfy that. So we won't always be able to do this, but a lot of times we will. So we make all inequalities true at the same time, simultaneously. The region in space that does this is called the feasible region. I probably shouldn't capitalize it. Feasible region. Right. I mean, it's called something else sometimes, but that's the more popular word for it by far. So I'm just going to leave it with that, the feasible region. Right. Yeah. So here's the a process for actually solving a system, which I mentioned verbally last time, but let's make sure we actually write it down so no one missed it. Is you're going to want to, 1, sketch all inequalities. 2, shade the overlapping region where all solution sets we learned how to find last class intersect. If there is no region where all solution sets, and it has to be all of them, every single one needs to be satisfied. There is no feasible region. Probably should be a little bit more specific. I'm a mathematics teacher, actually. So, process for solving a system. What system? Of linear inequalities. Okay, all right. That's basically it. So let's go. Let's actually jump into that and solve these so you can actually see what I'm talking about. Because that's the thing with being a math teacher. Like most of the time, people are like, what are you talking about? What is he talking about? What is he saying right now? Okay, so let me show you what I'm saying. So let's say we have to actually solve this system. Very simple system. There are only 3 inequalities of concern here. So nothing too crazy, but we are going to solve these. Okay, sketch a feasible region of the following systems. So what we're going to do is what we learned to do last time. We're going to start sketching stuff. So I'm going to sketch 1, of course. So I'm going to have my axes here. X, Y. I want to sketch X plus Y strictly less than 2. So that's going to be like the pro tip. You have to make the sound with your mouth or it won't be as accurate. So it has to pass through 2 and 2. Of course, you know this. You cover up your finger, one of the variables with your finger, and you solve for the other one. So you have X plus Y equals 2. Cover up the X, you get Y equals 2. Cover up the Y, you get X equals 2. And those are the numbers that you plot on the XY axis respectively. Now, of course, there are, so that was this guy. Now, I have another guy, this guy, X greater than or equal to 0. I need to sketch X equals 0. Well, that's the guy that's right along the Y-axis, right? So this is X equals 0. And at this point, it's very good to start labeling the things that you're drawing because you're going to be drawing several of them. So you're going to want to know who is who. That's going to be important. And then I'm going to draw this guy, Y equals 0. So that's just this line here. Now, we don't always need to sketch these. Because they're the axes. I'm doing it here for emphasis. But if you're already sketching the X and Y axis, so you don't really need to sketch a line on top of the line you already sketched. Like that's just overkill. Okay, so that's the Y equals 0. So now there are actually a couple ways of actually following up with this. Okay, and I'm probably, maybe I should show you the 2 ways. Okay, so a couple ways to shade these. One way to proceed. It's actually not the recommended way, but it's probably going to be the more instructive way for when I say the overlapping of the regions, what do I really mean? This is going to show you what I mean. However, in practice, you probably don't want to do this because you're just going to end up confusing yourself, right? So it's actually not the recommended way. Sketch, like I said, all solution sets. Find the overlap. Okay, so now that's what would that look like? Well, we know we want x plus y less than 2. I can use the origin as a random test point. If I plug in x and y equals 0, I get 0 less than 2. That's actually a true statement. So I know that the solution set is below the red line. So there's a solution for the red line. Going off like that. And then I do it for the x line, right? So this says x is greater than or equal to 0. That's already in the format where you know, oh, I should shade to the right of the green line. So then you go like so. And then you're like, oh, it's y greater than or equal to 0. So that's in the format that says I should shade above the lines. So I'm going to shade above all these lines. Right? And the solution is where all the colors intersect. Okay, so clearly you'll see there's only one region in space where all 3 shadings kind of overlap. That is going to actually be inside the triangle. It's going to be above the y-axis, to the right. It's going to be to the right of the y-axis, above the x-axis, and below the line, right? But as you can see here, it can get kind of confusing with all this shading all over the place. And this is just 3 very simple lines. Like if I give you like 4 or 5 of these things, and there's like shadings all over the place, and you have like 7 different kind of shadings, and you're like, I want to find the region where all 7 shadings overlap, then a region where 6 of them overlap is going to look pretty darn close to the region where all 7 overlap, and you're gonna make a mistake, right? So you can, this actually shows you what I'm talking about when I talk about the overlapping of the regions, but it's probably not going to be the recommended way. So yeah, so the solution is going to be the region that looks like this, combined with that, combined with that, right? And any region that doesn't have that kind of pattern isn't the solution. So for example, like up here in the top right corner, it only has 2 of those kinds of shading. It doesn't have the third, right? So that would not be in my solution set. The solution set is the triangle that's right here. Right, so feasible region indicated by that, everything inside that triangle, every point inside that triangle. Okay. Now, I mean, hopefully that's clear to everyone. Does everyone see what I'm getting at so far? Are we good? You see what I'm doing? Okay. So, so that's what it kind of means when you're doing it. However, in practice, you don't want to do this, like I said, because you could end up confusing yourself, especially when there's a lot of equations a lot of inequalities that you want to sketch. So what you can do is instead to a better way. Indicate with arrows where you would shade to satisfy each inequality, but don't shade until you see what the feasible region is. As indicated by the arrows. Okay, so what would that kind of process look like? Well, again, you go one by one for each of these guys. So we already realized that, okay, I want my solution region to be below the red line. What you would do is you'd write arrows along the red line, like right here. Okay, maybe I should do that in a different color. Pink, right? So I write an arrow that says I would shade in this direction. And I write it on the 2 edges of the line. And the arrows I'm using here are these guys, the pink arrows. So I know, yeah, I'm going to want to shade like in this direction, right? But I don't actually shade it, right? I'm just making that indication. Then I move to the next line, the green line, and I'm like, okay, I know I want to shade in this direction. And then I move to the blue line and I'm like, okay, I know I want to shade in this direction. Right? Which means the region that you shade must obey all the arrows. So it must be below the red, above the blue, and to the right of the green. And yeah, that's this part right here. Right? So here, the feasible region is the only region shaded by that in this case. Okay. So now I can say, yeah, everything inside this triangle is what I care about. including the boundaries on the vertical and horizontal sides, but not the boundaries on the hypotenuse. Okay. All right. So now what I want to do. Oh, never mind. Still want to do something else. So here is our next example. So I'm going to do this one a lot quicker, of course, because you guys now know what we're doing, hopefully. And then I'll get you guys to try some. So here we are. And so yeah, so here we go.
Didn't we just do this one?
No, it's slightly different. The first one was less than 2, x plus y less than 2. And this has x plus y greater than 2. So there is a difference, and I do want to emphasize something about this. So it's different, very similar but different, right? So sometimes when you want to talk about the nuances of a problem, it's nicer to just go back to the same problem and just look at it in a different way, as opposed to be inventing a whole new problem. You don't want your brain learning several things at a time. Multitasking isn't as good as people say it is. It's actually not great, right? So right now, you know how to get that picture. I don't want you worrying about how to get that picture. I just want you worrying about how do I examine that picture under these minor changes, right? So the picture is going to be, you know, we had this before. X plus y equals 2. And I know that I want to shade greater than and less than. So I have arrows here, and I have arrows here. Now with x plus y greater than 2, if I plug in the origin, that is no longer true, right? If I plug in x and y equals 0, I get that 0 is greater than 2, which is false, which means the origin is not in the solution set. So the solution set is actually this time above this line. So now, what is the feasible region? It is going to be the guy here. Right? So it's not the triangle. It's everything actually that's on top of the triangle that's in the first quadrant. Okay, so this is the feasible region over here. Now this brings up the notion of bounded and unbounded regions, which I probably should talk about. Right, but hopefully I indicated, you kind of would know how to get that. So the above bring up the notion of bounded and unbounded feasible regions. Okay, so definition. A feasible region is said to be bounded if a circle of finite radius centered at the origin can be drawn to include the entire feasible region. Otherwise, it is said to be unbounded. Okay, so to go back to our previous examples here, if we looked at example A, it looks like this, something like this. Notice that I can actually draw a circle. I can actually draw a circle that has center the origin. So let's say that's the center of the circle. And I can draw such a circle with finite radius so that if I center it at the origin, notice that the entire shaded region is actually included inside that circle, right? Like the entire shaded triangle fits inside that circle. And this means we have a bounded feasible region in the case of example A. Now, if we looked at the second example I told you about, no, that's not where it was shaded. Shaded above here, going on forever, then it's like no matter how big I draw a circle, right? No circle of finite radius can fit all the shading. These shadings are incorrect. They're above the x-axis. Okay. No circle of finite radius can fit all the shading. So it's unbounded. The region of the solution goes on in such a way that we can't bound it inside everything. It just goes off to like the magnitude of the XY coordinates go off to like infinity. They're unbounded. No circle of finite radius can bound all the shading. We have an unbounded region in this case. Okay. Right. So that's the difference between bounded and unbounded. Unbounded means like the size of the coordinates go off to infinity, and I can't contain them. Versus I can contain them. There's a biggest possible magnitude of coordinates that will work, right? And that's going to be important because we're going to have some theorems that are very different for bounded and unbounded regions when we want to solve certain things in 5.3. So there's that idea. So that's why I kind of slightly tweak these examples. It's just an example that Pastor Jhevon thought, it's great to actually introduce this concept by having them see it. So that's bounded and unbounded regions. All right, so now that leads us to the main event. So here are some examples. And I'm actually going to want you guys to take 5 minutes and do these. So I'm actually going to create some breakout rooms and put you guys in your groups. So I told you guys to figure out what your groups were. So hopefully you did. And you guys can tell me, like, how many groups were there even? Were there 5 or 4? I forgot. I'm going to create 5, but we might ignore one of these rooms. Okay, so maybe someone can chime in and tell me who is in their groups. Is Alberis here?
Yeah, I'm right here.
Yeah, who's in your group?
I don't remember everyone in my group, but I remember I was with Dafina.
Okay.
And yeah, that's all I remember. I don't know who else.
Does anyone else remember being in a group with Dafina or John? Are you in that group?
Oh yeah, I'm in that group, and Sixing is as well.
Sixing, okay.
Yeah.
Is that all?
I'm with...
Okay, so I'm going to assign you guys to that group. Okay, so the next group, Alexandra, is Alexandra here? Do you remember your group members? Seems like she's having trouble with the mic. Is Beckett here? Or Christine?
Yes.
Okay, so Christine, who's in your group?
I'm trying to see right now. I know John was in my group.
Oh, okay.
I think that's the only person I know for sure he was in my group. I'm not sure
Okay.
who else was in my group.
John, you remember anyone else?
Oh, I think Tom and Nick.
Tom and Nick.
Here.
I guess Tom is not here.
Oh,
Right.
I'm Tom. Yeah, that's me.
For some reason I don't see you in the list here. Do you go by another name? Like, I don't see Tom.
I go by Tom.
And that's what you're signed up in the room?
What room?
In the list of participants, is that the name that's there?
No.
Oh, you need to tell me then. What is your actual, what is the name that you're registered as?
Shiru, XIRU.
Shiru. Okay. Yeah. Who else is in the group? Okay, I'm gonna assign you guys there. Cole? Is Cole around? Or Seamus, who's in your group?
I think I'm with Beckett and Alexandra.
Okay. And I guess Ryan? or Sebastian?
Yeah, I'm here.
Yeah.
I don't know if I left early one of the classes where you made the groups, because I'm not aware of which group I'm in.
Okay. So, I mean, there are 4 people left over. I'm just going to put all 4 of you in the other group. So that's what we're going to do. So here's what we're going to do. So in group 1, we have Albira, Delphina, John McGovern, C. Jing. Group 2, Christine, John Kotsalonikis. The other John, and Tom. Group 3, we have Alexandra, Beckett, and Seamus. Group 4, we have Cole, Ryan, Savion, Sebastian. So group 1 do A, group 2 do B, group 3 do C, group 4 do D, and then all groups after doing the first one do the second one, do part E. I'm going to give you guys like 5 minutes, and then you come back. So there you go. You should see actually the groups popping up. I'll see you guys in a bit.
Professor, I'm in group 1, right?
Yes.
So we finished the A.
You're going to go into group 1 and you're going to do part A
Yes.
that you see on this screen. Yeah. So when you see the groups, you click on it. And Ryan, you should go to your group as well. And maybe I should actually also stop the recording. Okay, so everyone's back. Now, of course, we're not going to be able to get through all of these, but yeah, you guys should have, at the very least, your picture should look something like this, like the blue and the red lines. Is that, did you guys come up with that at least? And did you figure out? And did you figure out what this intersection point was? Just want to verify if everyone got at least that far. So in parts A, B, C, and D, the picture starts out looking like that. Did we get that? Did we find the coordinate, the green coordinate? Because that is something that you're going to want to find, and we'll see why. But for now, we're going to see that. We're going to do that. And next time, what I'm going to do is I'm going to ask you guys what position. So I wrote in some Roman numerals here just so that we can participate. So next time, you guys are going to pretty much tell me what number regions to shade for the answer that your group got. And we'll take it from there. That being said, we'll end right there. And we have some fun things to do next week. So not only are we going to get into 5.3 after these examples, but we're also going to learn how to do these on the computer, Excel and Python and stuff like that. Should be interesting. But for now, that's where we're going to end. Hopefully you got that. But let's make sure. Okay. That being said, thank you for your time and attention. We will end there. There are no questions. So yeah, I guess that's it. I'll see you guys in the next one. Ciao.